Good day guys. Alright, so in this video I want to show you the derivation for Young's double slit experiment, and then what I want to do is present to you a solution for one sample problem in which you can apply the equation that we derive in this video. Right? Okay, so first things first, let's consider Young's experiment, which has this simple setup. I have a double slit, I have a screen, and that's about it. And of course I have a light source that gives out parallel light. Alright, so because we're talking about dark and bright fringes, we want to know what sort of interference do you find at a certain point on the screen, right? So we want to know the path difference between them, because the path difference is going to tell us the whether or not it's a bright or a dark fringe that forms. Okay, so I'm going to draw three main lines, right? The first one, the yellow one, is the light waves coming from the first slit. The green line represents light waves coming from the second slit. What about the blue one? The blue one simply connects the point that we chosen on the screen and the midpoint between those two slits. The midpoint meaning halfway through, right? Okay, so once I have this picture, what I want to do now is label a few things. The first thing that I'm going to label is the angle between the blue line and the horizontal line. Okay, the horizontal just comes from midpoint to the screen. Okay, so I'm going to call that theta. The angle between them is theta. Okay, and then I want to label the distance between those two slits. All right, I want to also label the distance from those slits to the screen. And of course I label this as L, not D, because that gets very confusing. I'll just use L. And then last but not least, I want to connect between the point the horizontal line touches the screen and the point that we chosen on the screen, right? And we'll call that Y. Because we're talking about path difference, I would also like to know what is the path difference between them. And I'll just take it as a 90-degree angle there, right? That's going to be the path difference. I'll just label it here, difference. All right. Okay. So how do I go from here to mathematics? Okay. So one of the tools that we can use is what we call law of cosines. This comes from trigonometry. Just apply those sort of equation. Okay. So how can we apply that? Well, we can look at R being the blue line, the yellow line, and this half, right? So it's going to look something like that, right? So this is R. I'm going to label the blue one as R, the yellow one as R1, and this is to be D over 2. Okay, I can apply it there, right? And I can apply the law of cosines there. So what it will give me is R1 square equals to R square plus D over 2 squared, right? Minus dr cos pi over 2 minus theta. Okay, so because we see a pi over 2, we can simplify this cos into sine, and what we'll have is R1 square equals to R square plus D over 2 squared minus dr sine theta. Okay, so that's what we'll have. Okay, so what happens next is we want to apply that to R2 being the green line. Okay, so I'll just change the color here. I'll have R2 squared equals to R square plus D over 2 squared minus dr cos pi over 2. This time, because it's below, right, I'm going to have plus theta instead. So again, I can simplify this because as a pi over 2, I'll have r square, r2 square equals to r square plus d over 2 squared plus dr sine theta. So I'll call this equation 2, and then the first one being equation 1. Okay. Okay. So from here, what we can do is we can take the difference, because that's what we're looking for. We are looking for the path difference. However, we can simplify this a bit further. We can have, all right, r2 minus r1, so it's going to be just 2 minus 1, and that gives us r2 square minus r1 square, right? So it's going to be r2 square minus r1 square equals to 2 dr sine theta. That simplifies our work much um, easier, Okay, so at this point, what we want to do is consider limits. If I have my L much bigger than D, so I'm just going to put it here. If my L is much bigger than D, what I will find is that my R1 plus R2 is approximately 2R. Okay, so if it's approximately 2R, right, I can always expand R2 square minus R1 square, right, to this form. So R2 minus R1, and then multiply that with R2 plus R1 equals to 2 dr sine theta. Sorry about that. Okay, so R1 plus R2 is 2R, so I'm left with 2R R2 minus R1 equals to 2RD sine theta. I can cancel those out for both sides. So what I'm left with is the path difference between R2 and R1. R2 minus R1 equals to D sine theta. And that's going to be our delta. Okay? So that's our path difference. The path difference is going to depend on D and theta. So D being the distance between the two slits, and theta being the angle, from the midpoint of those two slits to the point on the screen. And we can make that by simply making this simplified assumption, or this assumption that actually simplifies our calculation. So if this d sine theta is equals to m lambda, then I will have constructive interference. If it's m plus half, it's going to be destructive. All right. So now what I want to do is I want to work out if I can relate y and L into this equation. So I'm just going to write down the last line again. So delta equals to r minus 1. So I'm just going to write here again. So delta, I'm just going to use a different color now. Delta equals to d sine theta equals to m lambda. For constructive, let's just work with constructive. Again, I want to remind myself that this is for constructive. And then once we know the equation for constructive, we can just add half to the order to get destructive, right? So if we have, sorry, If we have L to be much bigger than D, so if I have L much bigger than D, alright, so what we know is that we can also assume that D is much bigger than lambda, right? If that is the case, right, then we can assume small angle approximation, which tells us sine theta is going to be approximately tangent theta, which is going to be approximately y over L, right? So theta is just sine or tangent y over L. So what I'm left with is dy over L equals to m lambda. And this y is for the specific point that we have chosen. So I'm going to label there m, the position of the mth order, right? So what I'm left with, if I just rearrange that, I'll have ym equals to m lambda L over d. Okay? So that's our equation that relates the position of the fringe, the order of the fringe, the wavelength of the light, the distance between the slit and the screen, as well as the slit separation. Okay? So that is all. We have derived what we need, and then now all we need to do is apply it. Okay? Alright, so let's look at a sample problem. Okay, here is our sample problem, right? In Young's double slit experiment, suppose the separation between two slits is d equals to 0.32 millimeters. If a beam of 660 nanometers light strikes the slits and produces an interference pattern, how many maxima, right? Maxima being how many orders, how many bright fringes will there be in angular range? So again, maxima means bright fringes, minima means destructive interference or dark fringes. Okay, so what we have from before, we have, let me just write down solution here. I have the equation that we've got before, d sine theta equals to m lambda. I'll be using this one because they are talking about angles, right? What I'll have is m equals to d sine theta over lambda, right? I'll just substitute those values in. M equals to 0.32 times 10 to the power of negative 3, and then I'll have sine 30 over 660 times 10 to the power of negative 9. Alright, so 660 is a very common number that you'll see, especially when you're working with lasers, because 660 is actually in the range of red color, and it's very common to see red color lasers, at least nowadays, right? So once you calculate that, what you'll get is m equals to 242. So now the question is that the answer? No, because you have to remember that this solution gives us reminds us of a simple fact, which is we have drawn this picture before, right? And this angle in this particular calculation is 30 degrees, right? As you can see, the range is negative 30 to 30 degrees. So that means it's double that, right? So this is negative 30. It's double that. I have to double that. And then you have to remember that there is a bright fringe, what we call the central bright fringe. Okay? So then we can calculate the number of maxima, which is the 242. So number of central maxima will be 242 from this side, right? So this is going to be 242, and then plus the 242 from the bottom, and then plus the one central bright fringe. Now we have the total number of maxima in that angular range, which is 485. Okay, so the first 242 is from 0 to 30 degrees. The second one comes from 0 to negative 30 degrees, and then the 1, right? The 1 comes from the central right fringe. Okay, so that is your worked example. Okay, all right then. That is the end of the video. Thank you very much. I'll see you in the next video.